And this is the last part of 9.5, 9.5c. Hopefully I'll keep it short. Derivatives and integrals of power series. We will talk more about this later. Specifically, we're just looking at the intervals of convergence of these derivatives and integrals of power series. All right, so what happens if we have a power series and we just, say it's some function, f of x equals that power series, and we could write it out if we want to. All right, it has some sort of radius convergence, say greater than 0, and it has some sort of interval of convergence, c minus that radius and c plus that radius. Maybe it includes the endpoints, maybe it doesn't. And suppose f is a differentiable function. Right? So that means we could take the derivative of f. And if we took the derivative of f, this n would come down, and it'd be n times a to the n raised to the n minus 1. And we were starting at 0 before, so now we're going to start at 1 because if we plug in 0, it doesn't make any difference because we would get 0 here because n times a to the n would be 0. All right, so in other words, this first term actually goes away when we take the derivative. Right? It's a constant. So we end up getting something that looks like this. All right, so just remember, we can take the derivative now of just the power series. And again, x is our variable, so we're only taking derivative of this guy here. The a sub n does not change. It stays exactly the same. All right, we can also integrate, and when we integrate, we add 1 to the exponent, so we take this n and become n plus 1, and then we divide by that new n plus 1, and that's why we get this new n plus 1 down here at the bottom. All right, now when we integrate, we also always put plus c, so we have to add some possible constant in the front. If we actually know the integral of the function, we can solve for this constant pretty easily just by plugging in c. And all the other terms go away, and we'll just, whatever's left with this big C, capital C, different from lowercase c, by the way. All right, but the neat thing about this is the interval of convergence and the radius of convergence and the center all stay the same. So the radius is unchanged. The center is also unchanged. It's also still the same. So like we still basically have the same interval, c minus r and c plus r. The only question is what happens at the endpoints? Because it may change at the endpoint. So we may include it or we may not include it. I said that backwards, so we may not include it or we may include it. It could change from one function to the next. So the integral could be different from the derivative, could be different from the original function as far as what happens at the endpoints, but the interval will be the same length. It will have the same center and the same radius. It's kind of a cool fact there. All right, so here we go. Consider the function given by x to the n over n. All right, so what happens if we, well, look at the interval of convergence for the original guy, for its derivative, and for its integral. All right, well, if we integrate this, this would be c plus the sum from 1 to infinity of x to the n plus 1 over n times another n plus 1. All right, we're not going to worry about the c as far as the interval convergence goes, but with this guy here, we can do a ratio test, limit as n goes to infinity, of x to the n plus 2 over n plus 1 times n plus 2, so if I plug in n plus 1, that's what I get, times n plus 1 over x to the n plus 1. We want that less than 1. The n plus 1s are going to cancel out. We're going to have one extra x on top like we always do. So we're going to have the absolute value of x times n over n plus 2 is less than 1. And we're taking the limit as n goes to infinity. Well, this guy here is just 1. So we get the absolute value of x is less than 1. So we're going from negative 1 to 1. All right, we can plug in the endpoints and see what happens. For each endpoint, we'll have an n squared on bottom, so it'll be similar to like n squared on the bottom, which converge for both endpoints. So both of them are going to converge, and there we go. All right, next up, if we look at f of x, the original guy. All right, well, it should be the same interval. We just really have to check the endpoints. If you want, we can show that it's going to be the same interval by doing the ratio test with this guy. So if we do the limit as n goes to infinity of x to the n plus 1 over n plus 1 times n over x to the n, and that needs to be less than 1. We're going to have an x on top and n plus 1 on the bottom. The x is still an absolute value. We are taking the limit as n goes to infinity. which is almost exactly the same thing as we had here. This goes to 1. So we get the absolute value of x is less than 1 again. So again, that was our radius 1. Our center was still 0. So we're going from -1 to 1 yet again. All right, but if we check the endpoints now, let's see. If we plug in -1 here, we'll have -1 to the n over n. That's an alternating series. That converges. LT. All right, but if we plug in just regular 1, we have 1 over n. That diverges. All right, that's the simple harmonic. So we include the -1. We don't include the 1, so that's different. So this guy, -1 to 1, not including that. This guy, -1 to 1, including both. And if I continue going with my color trend, red, then purple, obviously blue comes next. If we look at the derivative now, so we take the derivative, we bring down the n, so we'll have the sum we bring down the n, it'd be n, x to the n minus 1 over n. Those are going to cancel. All right, so if we can do the ratio test. We actually don't need to. We could just do the geometric series, but again, if we do the ratio test, we've got x to the n over x to the n minus 1. All right, if we plug in n plus 1 there, we get n. This will cancel out completely, leave us with 1x on top. The absolute value of x is less than 1. Exactly what we had for all the other ones. Right? There it is there, there it is there, and there it is there. So we get -1 is less than x is less than 1. We can try both endpoints to see if they work. In this case, in this original guy right here, if we try -1, we'll have the sum of -1 to the n minus 1, which oscillates, it diverges. And if we try 1, we get that, which also diverges. It's just 1 over and over and over again. So for this one, we don't include either endpoint, and we just say it's -1 to 1. So again, we get 3 intervals. They cover the same section, but they all do different things at the endpoints. So really the endpoints are what you have to check. Right? We'll have the same interval, just check the endpoints. So we could have just found the interval for one of them and said, okay, it's going to be the same for all of them. Let's just check the endpoints. And there you go. Much shorter problem. All right, so that's it for derivatives and integrals. Check out the homework. It is posted on Google Classroom.